So last time we have introduced a new intuition for tangency and realized that in mathematical language it can be expressed as a local linear approximation. So our tangent should be the best possible approximation to points in the neighborhood. And we have also proved that this approximation exists. So here a is a constant if and only if the derivative at this point exists and is finite. And moreover, if it does exist, then we know that this constant is actually f prime of x. So that's why I have crossed it out here, because when we write this approximation, we do not know for sure that this linear constant is actually equal to f prime. But once we prove that f prime exists, we know we can replace it by f prime. In other words, f prime is the slope of a line at f of x that guarantees the closest linear approximation. So what happens in two variables? We have a function that depends on x and y and gives us some point z for every pair of x and y. So here's my surface corresponding to function values of f. I pick a specific point, x naught, y naught. So this point is x naught, y naught. It gets mapped to this point, and as you remember from definition of partial derivatives, what we do is we cut our surface along this plane. It's a vertical plane that goes through y naught and x naught, y naught, and it creates this curve. That's how it slices our surface. But this curve, this is a curve in x, z coordinate system, yes? So if you look at this curve from this direction, it will be flat and it will be on a plane, right? So we can apply single variable calculus to it, and derivative of this function at this point, of this curve at this point, will be our partial derivative with respect to x, because y is fixed and x is allowed to vary. So now, instead of having a neighborhood defined just along a curve, we have a neighborhood defined around the point. But of course, if we pick a point in the neighborhood, we will be able to understand it by how its projections onto x and y axes change. In other words, we have a new point where we increase x slightly, so this is x naught, and we increase y naught slightly, and we want to approximate it in a similar manner as in single variable stuff. So we should get that it's f of xy, and then we add changes that partial derivatives bring us. So we want to evaluate partial derivative with respect to x at a point x naught, y naught times delta x plus f at y, x naught, y naught, delta y. And we, of course, do not want to forget about the error terms. So we want to add functions that decrease faster than these increments as we tend them to 0. So delta x, delta y go to 0. So the question now is, when is it true? And here's a very important point which we should stress. In single variable case, existence of a derivative was enough and it was sufficient. But now, simple existence of partial derivatives is not enough. So existence of f of x, partial derivative of x, and fy is not enough. If you want to see examples of when they exist but are not continuous, look at part 4. So what I mean is, we also require f of x and fy to be continuous on some neighborhood around x naught, y naught. So if this holds, then we know we can rewrite our approximation in this manner. And that's what we are going to prove. So we have a theorem. If these partial derivatives exist at some neighborhood of x naught, y naught that includes this point and are continuous on this u neighborhood, then, well, this linear approximation holds. So let's prove it. We know that if we subtract f of xy, f of x naught, y naught, sorry, from the right hand side, we get a total change of a function. So we now have this. Right? So we want to show that this difference is equal to this expression. But since I want to use my partial derivatives, I actually want to rewrite it in the following way. I still have my first term, but then I add this guy, and then I subtract it, because if I keep it, then I will change my expression, right? It will not be inequality. So I add it, then I subtract it. Sorry, so of course, here I mean y naught plus delta y naught plus delta y. And then I do not forget about my last term. So now if I group them slightly differently, so if I rewrite it again, I'll have big brackets of x naught plus delta x, y naught plus delta y, minus f of x naught, y naught plus delta y. So I'm just subtracting this term first, and then I want to group other remaining terms like that. I want to do x naught, y naught plus delta y, minus f of x naught, y naught, right? But now, observe how in this bracket, the y component is unchanged. It's y naught plus delta y, so assuming delta y is fixed for now, it's unchanged, and it's only x naught that receives an increment, right? So this is like this resembles partial derivative with respect to x at x naught y naught plus delta y, right? If you are unsure about this, then you should recap your partial derivatives. And here, x naught is fixed and y naught receives an increment. So this looks like partial derivative with respect to y at x naught, y naught. So notice how these partial derivatives are happening at different points. So this reminds us of a partial derivative times our increment, but more precisely, if we recall mean value theorem, what can we say? Well, as delta x decreases, we enter our neighborhood of continuity. So we enter this space around x naught, y naught, at which f of x was continuous. And remember, if a derivative is continuous, the function is also continuous. So at some point in our neighborhood, we can apply mean value theorem to this function because, once again, it can be considered as a function of one variable for fixed delta y. So in other words, if delta x is small enough, there exists a c in x comma x naught plus delta x such that f of our endpoint x naught plus delta x y naught plus delta y minus the starting point x naught y naught plus delta y divided by delta x is equal to f prime at c, but of course here I mean a partial derivative with respect to x. Now for convenience, we know that since c is between x and x naught plus delta x, we can rewrite c as x plus some theta times delta x, where theta is not greater than 1, right? Because if this point is in between, it means we are not adding full delta x, but part of it. So now we have this expression, and taking all this away, we can continue our equality, and it becomes f prime of x at, so this was abuse of notation, right? So here I will have x naught plus theta delta x, y naught plus delta y times delta x, and I can apply the same argument to this part, but now I will have a partial derivative with respect to y. So I will have y x naught stays the same, and I'll have y naught plus some theta dash delta y times delta y. So now, again, using continuity, yes, so continuity allows us to take limits that exist inside, outside, as delta x and delta y tend to 0, which happens inside, we can take that limit outside. We get that this term tends to simply f of x at x naught, y naught, and this term tends to f of y, x naught, y naught, which is exactly what we need. So let us recap what's going on exactly in our calculations. We have these two curves that resulted in slicing our surface. This is a curve in xz coordinate system. This is a curve in yz coordinate system, right? So they are straight lines because I'm looking vertically down on them. You can look at the drawing if it's not clear. So then we have a starting point, x naught, y naught, and we give increments along both directions to get a new point, x naught plus delta x, y naught plus delta y. And we want to be able to approximate it in the best way using linear maps. So what it means is, in a single variable case, we deduced that a tangent was the closest linear approximation. But here, we have a plane that's generated by two tangents, if you like. So we have a tangent along x, tangent along y, and we want their summation, their combination, to be the best linear approximation. Best means that the remainder, after we add these two terms, that the remainder is negligible compared to delta x and delta y, when delta x and delta y are small. Right, so we want this difference to be that, but so far in this video we got to this point, and we know that by continuity this term tends to f of x at x naught, y naught, which we need, and likewise here. So now just use properties of limits. So the way limits are defined tells us that this term is its limit value plus some function, let's call it alpha, that depends on both delta x and delta y. But what do we know? Since if we take a limit on the left-hand side, this guy tends to this guy, this function has to tend to 0. So this guy tends to 0 as delta x and delta y tend to 0. Likewise, for this limit, we have x naught, y naught plus theta dash, y naught is equal to f of y, x naught, y naught, plus, let's call it beta, and actually here it only depends on delta y, because x naught did not receive an increment. And this guy tends to 0 as delta y tends to 0. So this is just from the definition of a limit, right? So this allows us to rewrite our difference in function values taken at a new point and at a base point to get this partial derivative times delta x plus this guy, x naught, y naught, times delta y, plus, don't forget about these guys, alpha, delta x, delta y, again, times delta x, and then beta, delta y, delta y. Okay? So we are done because these functions are in O little of x, delta x, for example, and this guy is in O little of delta y. So if you're not sure, then just take a ratio of this whole expression and delta x, and we know that this function tends to 0. So it is indeed some small function which depends upon delta x, just like here. So we are done. But it's important to now state certain definitions. So if our two-variable function has this property, so it has best linear approximation at all points, or actually for now, let us write at a specific point x0, y0. So this just means that we can rewrite points in the neighborhood like that. Then this function is called differentiable at this point. So if this linear approximation exists at all points of the domain of f, then it is differentiable, just differentiable, without us attaching this definition to a specific point. So the reason is because the main change, the main component of a change of this difference is coming from linear terms with respect to delta x and delta y. So this is a differential, this is a differential. These are terms that are linear in delta x and delta y because derivative stays fixed. So we have expressed this difference as a combination of linear terms plus terms that decay faster. So differentials give us the biggest part of the change. So this is crucial to realize. So differentiable and derivatives are related, but is not the same thing. Once again, in this video we proved that continuous partial derivatives in x and y imply differentiability. What about another direction? Well, here's what we can say. If we again take our function and we want to know this difference, and if we know that we can rewrite it like that, plus O delta x plus O delta y, then A and B are constants, yeah, these are constants. So if we can write it like that, if we can write this difference as a sum of linear terms and higher order terms, then it is necessarily true that A is indeed partial derivative with respect to x and B is fy. So this is important, okay? In some sense, what I have shown in this video is that if we have continuous partial derivatives, then this is true and these are constants. But if we assume that we don't know the existence of partial derivatives yet, but we know that a function has the best linear approximation, that then this approximation necessarily arises from partial derivatives. And this is a good exercise for you to do in order to fully grasp the difference between differentiability and derivatives. So an important thing to note here in this exercise is that differentiability will imply existence of derivatives, but they will not necessarily be continuous. So multivariable case is really different from single variable case. And look at part 4. If you want to see examples of functions where we prove that this system of implications is correct and it can't be extended,